Welcome back. Now we're going to talk about types of reactions. We're going to start with oxidation and reduction reactions. It's not the next thing in your textbook, but it's in there somewhere. And there's going to be two parts to this. First, we're going to talk about oxidation and reduction reactions involving inorganic compounds. These are compounds that don't contain carbon. Most of them are going to involve ionic compounds. So we're going to see a metal or ammonium in them somewhere and take a look at what happens to them then. The second part, we're going to talk about oxidation and reduction reactions with organic compounds. So those are all going to be compounds that contain carbon. In either case, the term oxidation means the loss of electrons from an atom. Oxidation is the loss of electrons from an atom. Reduction is the gain of electrons by an atom. Both processes occur together in a single reaction called an oxidation reduction or redox reaction. A redox reaction involves the transfer of electrons from one element to another. Now, we saw something like this when we formed ionic bonds, but this is a little bit different because we won't necessarily create new bonds between the guys who have lost electrons and gained electrons. They may just stay with their own group that they came with, but it will be the same electrons that are lost by one element that are gained by another element. The redox reactions always have two components. One element that's oxidized, that loses electrons, and one element that is reduced, that gain those electrons. Okay. Continuing with the inorganic compounds, an easy trick for identifying many inorganic redox reactions, if you're given a chemical equation, check and see if there's a single element in it. If so, it's a redox reaction. If you see a neutral element by itself on either side of the arrow, it could be a reactant, it could be a product, or you might see a single element by itself on the left and another one on the right. However it goes, a single element is a redox reaction. Examples of these single neutral elements. The metals. Metals are written as monoatomic, meaning one atom, and they are solids at room temperature. The only exception to this is mercury. Mercury often exists as two, and he's a liquid at room temperature. But you will often see something like sodium, Na, and solid, K with an S, silver, zinc. All of these are solid monoatomic atoms at room temperature, and they're all neutral. So there's no plus sign next to any of these, or +2 in the case of zinc. The nonmetals, we've talked about in chapter 4, another flashback. 7 elements exist as diatomic molecules. So if I see just Br2 on one side of the element of the equation, that's a single element, and that would mean it's a redox reaction. Or if I see I2 on either side, or N2 or Cl2, my Brinkelhoff group. These guys by themselves, they're a single element. It's more than one atom of that element, but it's a single element. If he's on either side of the arrow, it screams redox reactions. And I just need you to trust me on that because we're not going really far in depth with this idea of oxidation reduction. I'm just trying to hit the highlights and make sure that you can recognize an example of a redox reaction where you know someone's been reduced and someone's been oxidized. There are several main types of reactions. Some of these are always redox reactions, meaning they always will have a single element either on the left side of the arrow or the right side of the arrow, or both. Some of these types of reactions that we're going to look at will never be redox reactions. They'll never have a guy by himself on the left or on the right. I want you to help me out. See if you can identify the following 6 types of reactions as sometimes, always, or never redox reactions. Keep an eye out for those elements by themselves. Let's start with synthesis reactions. The lab, I noticed, also calls them combination reactions. I think they might even be called addition reactions, but the more common name is synthesis reactions. To synthesize something means to make it, to create it. A synthesis reaction is the joining of two or more reactants to form a single product. The synthesis reactions are also known as combination reactions. How do I know if I have two or more reactants? Well, I either see two names of compounds, or in the equation, I see a plus sign. At least one plus sign means we have at least two or more reactants. On the right-hand side, there's no plus sign, so it's just one product on the right. Sometimes we represent this as A plus B forms AB. There's no element A. There's an element B, but for boron, but that's not what they mean in this case. An example, we could take 8 iron atoms, Fe stands for iron, and a molecule of sulfur, S8. So I have 2 reactants here, and they're combining to form 8 groups of, this is iron 2 sulfide. Together, we have just one product. You might have multiple groups of that product, but it's one product. 2 going to 1 synthesis reaction. Do you see how synthesis reactions could be redox reactions, but not always? Is this one a redox reaction that we have here between iron and sulfur? Sure, I have just the element iron, so that would make it redox. We also have just the element sulfur. We have 2 times the money that this is a redox reaction. In fact, later we'll see that the iron is reduced and the iron atom is oxidized and the sulfur atoms are being reduced. Decomposition reactions. This is the opposite of synthesis. Like a decomposing body where it's one body starts breaking down into multiple parts. A decomposition reaction is the conversion of a single reactant to 2 or more products. No plus on the left side, just one compound. And we have a plus side on the right, so we have at least 2 products on the right. 2 groups of water breaking apart to form 2 molecules of hydrogen gas and 1 molecule of oxygen gas. One product forming one reactant forming 2 products. Decomposition reactions are often redox reactions, but not always. Sometimes a big guy will break up into 2 smaller guys that are not individual elements. So this one is a sometimes group. Is this example a redox reaction? Sure it is. Hydrogen is just one element. Oxygen is just one element. If I see an element by itself, a single element, 1 capital letter in the formula, then I know it's a redox reaction. A single replacement or single displacement reaction. This type of reaction is one in which one element replaces another element that's in a compound to form a different compound and element as products. So with our generic element A has come across the couple BC, and I guess C thinks A is pretty cute and they break up. B's out on her own, and A and C have now joined together as a new compound. We had a single element here with A. Now we have a single element here with B. This is a single replacement or single displacement reaction. One guy's kicking out another guy. Magnesium plus copper 2 sulfide forms magnesium sulfide and a neutral copper atom. This single element is becoming part of a compound. This compound broke apart, and now we have copper all alone. This is an example of a single displacement reaction. And do you see how these will they sometimes always or never be redox reactions. We're always going to have an element by itself on the left and an element by itself on the right. It's definitely always going to be a type of redox reaction. Single replacement or single displacement reactions are always redox reactions. They'll always have two elements by themselves, one on each side. Combustion reactions, we've talked about these a couple times now. In a combustion reaction, oxygen reacts with elements to form oxides and a lot of heat energy, so fire. Oxygen, O2, with carbon forms carbon dioxide. With hydrogen, it forms water. And with metals, oxygen forms metal oxides, like that aluminum oxide. That was when we were learning how to balance formulas back in chapter 3, Al2O3. This is a combustion reaction with an organic molecule, C10H8, is reacting with 12 molecules of oxygen gas. They're going to form 10 molecules of carbon dioxide, 4 molecules of water, and a bunch of heat. That's decane. A little bit of that will be in your fuel. Here's one with a metal. The 4 atoms of aluminum will react with 3 molecules of oxygen, and we'll end up with an ionic compound, the aluminum oxide. And again, we're going to make some heat. These are both examples of combustion reactions. Oxygen will always be one of the reactants, and then somebody else. So if O2 is always one of the reactants in a combustion reaction, will we say that combustion reactions are sometimes, always, or never redox reactions? Okay, O2 is always there on the left-hand side. He's always present as a single element. If there's a single element, it's a redox reaction. Combustion reactions are always redox reactions. Double displacement reactions, also known as double replacement reactions. This is one of the ones that is never a redox reaction. That's because we're going to have cations and anions in 2 different compounds switching places, forming 2 new compounds. We'll never have anybody by himself. The generic AB plus CD, they show up at a party, they mix and mingle, and A leaves with D and C leaves with B. Notice how the A and C, the guys on the left, the cations with a positive charge, they've switched places. So now the A is with the D and the C is with the B. Here's lead to nitrate reacting with potassium iodide. The PB, the peanut butter, the lead, is leaving the party with iodide. So we have lead to iodide. And the potassium, well, he's been jilted. The nitrate, been kicked out. And so now those guys will hang out together as a new compound. They'll never have anyone by themselves. So double displacement reactions are never redox reactions. The acid-base reactions are a special type of double displacement reactions. They will always have a hydrogen ion, H+, where the hydrogen ion just has a proton left. His electron has left the building. That H+, called a proton, in the acid is reacting with hydroxide in the base. And together these guys form what's known as a salt in water. A salt is just an ionic compound. Sodium chloride's famous salt, right? But he's an ionic compound. Salts are ionic compounds. We'll see this some more in chapter 9. But I want you to be careful. Acid-base reactions are a special kind of double displacement. Do you see how I'm not ending up with 2 ionic compounds on the right, like I did up here? Instead, with an acid-base reaction, you'll always form water. So we're going to keep an eye out for when we form water after we start with these 2 compounds on the left. we are going to play a game, a new game. This time, the game is figuring out what type of reaction is taking place. Move this image, not sure what it looks like for you. It might just be a black box. For me, it's my face. So we're going to follow this series of questions. We always start with the first question. When we can answer yes to a question, we're going to stop. So we've been given a reaction. Either it's going to be in words, like hydrogen gas and oxygen gas react to form water, or we'll be given H2 plus O2 goes to H2O, just chemical formulas. Either way, we're going to start with asking, does your reaction have oxygen as one of its reactants, and either carbon dioxide, water, or a metal oxide as products? If yes, then it's a combustion reaction. Okay. In fact, usually what I start with is just saying, does your reaction have oxygen as one of its reactants? That's usually enough to answer the question. In this case that I was just saying out loud, H2 plus O2 goes to H2O. Well, look, we have O2 on the left, and we're forming water when it reacts with hydrogen. So heck yeah, that is a combustion reaction. In fact, it makes a huge bang and releases energy, a lot of energy from it. Okay. I think we would think of it as a combustion reaction. There's not usually fire though, but it's all right. We can work with that. All right, here we have another question. Let's say we said no. So what would be one? Say we have nitrogen plus hydrogen forming ammonia. Okay, so N2 plus H2 form NH3. Oxygen's not one of the reactants. So we need to go on to the next one. Does your reaction have two or more chemicals combining to form one chemical? If yes, then it's a synthesis reaction. Why, yes, nitrogen plus hydrogen. That's a plus sign. There's two reactants forming only ammonia, one product. That tells me that that is a synthesis reaction. But let's say we had another example and we said no. Well, then we'd go to the next one. Does your reaction have one large chemical falling apart to make more than one smaller chemical? If yes, then it's a decomposition reaction. What was an example? We saw water going in reverse. If you put, say, electricity, flow electricity through water, an electrolysis reaction, it will form hydrogen gas and oxygen gas. One guy forming two guys. That would be a decomposition reaction. Does your reaction have any molecules that contain only one element? Now, you're going to get to this one if you've said no to everything else. If we've reached this point and we have somebody that's by themselves, then it's a single displacement reaction. In fact, by the time I've reached here, I'll have one element by itself on the left and another element by itself on the right. Let's say we say no to this, so we keep on going. And then at this point, after we've said no to everything else, we'll be asked if our reaction has water as one of the products. If yes, then we're finally up to an acid-base reaction. However, if we've gotten this far and still saying no, then we haven't said yes to any of those questions above, we've got a double displacement reaction. You must do these in order. You can't just skip to the end. You've got to go through them one at a time. Keep saying no all the way to the bottom, then you're left with double displacement. A mistake I see a lot is for people to somehow skip this step where they check to see if there's water, and so they'll tell me it's double displacement when in reality it's acid-base. We can do better than saying double displacement. We can let them know it's acid-base reaction. There are several worksheets and answer keys here, plus I have posted something for you, a couple of ones that are on the chapter 5 section on Moodle, where I have some practice problems and the answer keys. I have mnemonic tricks to help you with these redox reactions. Remembering what's oxidized and what's reduced, you can think of oil rig. where oil stands for oxidation is loss of electrons, and reduction is gain of electrons. My favorite is Leo says grr, because I imagine this cute little line going grr. That one's kind of ferocious looking. The Leo is loss of electrons is oxidation, and the grr is gain of electrons is reduction. I bet the picture is going to say grr. All right. How about we say, that could be our passcode for this one. And my favorite is Leo says grr. That's our password or passcode or whatever that you're going to be asked for participation. Leo says grr. The last one, Elmo. Electron loss means oxidation. So if you're a big fan of Elmo, you've got that one. I'm assuming then that you just kind of have to remember that electron gain means reduction. There's no good edge of character to remember. And less fun that I thought of was oxidation, loss, and lose all contain the letter O. But then that, of course, means that gaining electrons is reduction. Here we have an example of a reaction. The neutral zinc, with an invisible 0 for his charge, has become zinc 2+. How do you go from being neutral to having a +2 charge? This is what we did a lot in chapter 3. Do you remember? Do we gain electrons or lose electrons? The electrons have a -1 charge each. If I lose them, I'm losing some negativity. I'm feeling more positive. So my zinc has lost 2 electrons. That's what gives him a +2 charge. Well, here is a copper ion and 2 electrons hanging out. What do you say he's missing 2 electrons here? That's what gave him a +2 charge. If he takes those electrons and gains those electrons, he'll form a neutral copper atom. Copper will gain those 2 electrons that zinc lost. Well, the neutral zinc lost 2 electrons to form the zinc +2 ion. So the zinc on the reactant side, he was oxidized. He lost electrons. What about the copper 2+ ion? The guy on the left, he gained electrons. So what happened to the copper ion? Yep, he's reduced. We're just going to focus on the guys on the left to say who is oxidized and who's reduced. This process is different, though, than a non-metal taking electrons from a metal and forming an ionic bond. This was a neutral metal atom giving his electrons to a charged metal ion. And these guys will be in separate forms. The copper 2+ will be part of a compound, an ionic compound. And the zinc will end up in an ionic compound on the right. They're not forming a bond together. So let's see, what else did I want to say? So we can write these processes as individual half reactions. The oxidation half reaction will be where the zinc forms the zinc ion and 2 electrons. The 2 electrons that were lost end up as a product. They got kicked out. Then for the reduction half reaction, the copper 2 ion gained or added 2 electrons. So those guys are going to go on the left. When you gain electrons, you write them on the left-hand side. That'll leave us with a neutral copper atom on the right. Here I'm putting in the zeros to show you that the neutral zinc became zinc 2+. Note how the oxidized species, so it could be an atom, a neutral atom like in the case of zinc, or my species could be an ion, like the copper 2 ion. The oxidized species gets more positive. When they lose electrons, they become less negative. The reduced species, which in this case was the copper 2+ ion, got more negative when it gained electrons. It's less positive now. It went from +2 down to 0. A compound that is oxidized while causing another compound to be reduced is called a reducing agent. The zinc reduces the copper ion by giving him electrons, letting him gain those electrons. Zinc acts as a reducing agent because it causes the copper 2+ ion to gain electrons and become reduced. A compound that's reduced while causing another compound to be oxidized is called an oxidizing agent. The copper 2+ acts as an oxidizing agent because it causes zinc to lose electrons and become oxidized. So it's kind of a give and take kind of thing. Here, you take these. Oh, no, here, let me take those from you. How convenient. And here's a list of oxidation reactions with the metals. They go from being neutral to having a positive charge. With my non-metal ions, if they lose electrons, they become neutral. Over here, my neutral nonmetals, they want to gain electrons and have negative charges. And if I have some metal ions and they gain electrons, they end up being neutral. Again, note that oxidation makes ions that are more positively charged. They're less negative. And reduction makes ions that are more negatively charged, less positive. I might actually go in here and point out ions or atoms that are more negatively charged or less positive. What else do I want to show? Oh yeah, just a reminder, if you lose electrons, they end up on the right side. If you're gaining electrons, they end up on the left side. When iron rusts, this is a redox reaction. The metal atoms, the iron metal atoms, react with oxygen and moisture in the air, and together they make rust, iron 3 oxide. The neutral ion reacts with the neutral oxygen, and they make ions. All right, take a look. Who got oxidized? Was it the Fe or the O2? When you're oxidized, you lose electrons, you lose negativity, and become more positive. The neutral iron atoms became +3 ions. They lost electrons, 3 to be exact. So the guy who gains them are those oxygen atoms. They gain electrons, which have a negative charge, so they become more negative. They are reduced. The neutral metals are always solids, and except for mercury, and they always get oxidized to positive ions. Remember back in chapter 3 when I said our metals always lose electrons and become positive ions? Still seeing it here. If I start out with a neutral, not one with a charge, but a neutral guy, it goes to that. What's different here is you're seeing the entire compound this time, where overall we have a neutral compound. I have to be able to look at this and see that in the Fe2O3, there's +3 iron ions and -2 oxygen ions. This is the second part of oxidation and reduction reactions. For these, we're going to talk about the ones in organic chemistry. In this case, we don't really see, it's all covalent bonds and stuff. So we're not going to see any +1 charges or -2 charges. Instead, what we'll keep an eye out for are bonds to hydrogen and bonds to oxygen. In the process of an atom being oxidized, it will lose a bond to hydrogen first. Then it will gain a bond to oxygen. Does that make sense that it's being oxidized by gaining a bond to oxygen? The only deal is you're going to have to lose a bond to hydrogen first. So here I see the carbon loses 4 bonds to hydrogens, and gains 4 bonds between the 2 oxygen atoms. Okay, the carbon and that molecule as a whole, we say is oxidized. And then our molecule of O2, the oxygen has lost its bond to itself, to an oxygen, and then it gained a bond to hydrogen, or 2 bonds to hydrogen atoms. So that's reduction. The agents are reagents. That helps me remember that the oxidizing and reducing agents are always going to be my reactants. The reactants, another name for reactants, are reagents. And so I see the carbon losing the 4 bonds to hydrogen and gaining back bonds to oxygen. Carbon has been oxidized. So the CH4, the methane molecule, is which agent? If it's getting oxidized, it becomes the reducing agent. The agents are opposite. Carbon is oxidized. The reactant with the carbon in it is the reducing agent. All right, so oxygen, O2, the oxygen atoms were reduced. They lost bonds to oxygen atoms, gained bond to hydrogen atoms. What type of agent does that make the oxygens if they were reduced? It makes them oxidizing agents. I guess it's not so surprising that oxygen would be the oxidizing agent. That's kind of handy. Almost at the end. Free radicals. Woohoo! We're free. We're going to watch a free radicals and antioxidants video. Now mine's going to be choppy because I need a new computer. If you want, you can rewatch it again without all the breaks in it, but I'm going to want you to watch it with me. And we'll have this overview. I believe this is the last page. Oh, no, we've got this exciting one. So we'll come back to this after the video. Here we go.
What are antioxidants and free radicals? Antioxidants are chemical substances found in fruits, vegetables, and spices that fight against the harmful effects of free radicals in the body. Free radicals are molecules in the body that are...
Okay. It's going a little too fast for me, so what am I going to do? I'm going to hit this button here for settings, and I'm going to do the playback speed, and I'm going to slow it down to 0.75. I'm also going to go ahead and set up the subtitles or closed captions. We're going to rewind just a little bit and hit play again.
The harmful effects of free radicals in the body. Free radicals are molecules in the body that are missing one or more electrons and as a result steal them from other molecules in the body, which then turn them into free radicals in a process known as oxidation. This causes an endless cycle of free radical formation. Antioxidants, by having excess electrons that they then donate to free radicals to make them stable, stop the cycle of oxidation. If the body does not have enough antioxidants to handle the production of free radicals in its system, or if there is an overproduction of free radicals, then it will result in the destruction of DNA in cells, which can accelerate aging and cause cancer and other diseases. To prevent these harmful free radicals, we must eat our fruits, spices, and vegetables.
All right, public service announcements. Courtesy of...
Created using Powtoon.
All right. Thank you, Powtoon. Here is an example where there's a normal oxygen atom and something's happened. It's been exposed to some sort of external environmental damage, and the oxygen atom loses one electron and it hasn't become stable. And in fact, it's become even more radical. It's got an unpaired electron now and it's unhappy. So what he does is that atom goes running around and finds another atom that it can take an electron from. So now he's more stable than he was to begin with, but he's created a new free radical. So that free radical goes out, finds somebody to steal an electron from, becomes stable himself, but now there's a new free radical, and so on and so on. And it's showing here that it can destroy our cell membranes, which means the cell is going to die and it causes early aging. And how to stop it? Well, something known as an antioxidant will have some atoms in it that have an extra valence electron. They can give up that valence electron and still be stable themselves. So when they give away their electron, they don't become a free radical themselves. They had something extra there to give. That then stops that last free radical in its tracks. It was hunting down an extra electron and now it's been given one. So he's back to where he started and the antioxidant's fine. He doesn't have an extra electron anymore, but he's also not down by an electron. It's like we stopped the zombie invasion. Yay. That's one of my favorite questions to ask about is how an antioxidant works. And the idea is they have atoms with extra electrons that can be given to the free radicals. They don't become free radicals themselves. And these are some things that can cause free radicals to form. Ultraviolet light, so light from the sun, and something to do with metabolism, with forming energy, it looks like, inflammation, air pollution, smoking, ionizing radiation. All of these can cause these free radicals, which in turn damage the DNA and again, cause early aging. That was something that at least one of the department chairs wanted you guys to know about. Whether, I can't remember, or I don't know if it was histology or medical lab tech or culinary, at least one of your groups needed to know about free radicals. And hence we've done this whole section on oxidation and reduction and learning about these crazy free radicals and the antioxidants that stop them in their tracks. Thank you for watching, and yeah, I'll see you in some live sessions, hopefully, to help you finish practicing all these concepts.